Sorry. Okay, let's start answering practice problems on the applications of first and second law of thermodynamics. Let's just have a brief recap of the kinds of questions we'll be encountering. So essentially, we have closed and open system. For closed system, uh, actually there's not much, no, when it comes to closed system. The only thing you have to note is for the energy balance for closed system, the one at the left is the internal energy change, as opposed to if your system is open, then that left side would be entropy change instead. Okay. Uh, yeah. So basically, we have two scenarios for closed system. One of them being the piston cylinder assembly. In this case, the volume is not constant. Another scenario that belongs to closed system is rigid vessel. That is, volume is constant. Okay, so just remember those two things for closed system. For open system, thermodynamic devices, either involving shaft work or not. Also, steady state and transient state. That's also under open system. Actually, still, steady state could still be applicable for closed system. No? I think that's the case, no? Yeah. Okay, so let's now go to the examples. Let's say 2 kilograms of water. Let me just draw the diagram. So, 2 kilograms of water at 120 degrees Celsius with a quality of 25% has its temperature raised 20 degrees in a constant volume process. So rigid vessel, no? Because the process is constant volume or isochoric. So we have constant volume, so there has to be a tank of some sort. 2 kilograms of water. Water is our substance right now. At 120 degrees Celsius with a quality, so this is X sub 1, 25% has its temperature raised 20 degrees Celsius. So that's going to be 140 degrees Celsius here. What are the heat transfer and work in the process? So that's what's being required now. Required, we have heat transfer and work in the process. This is state 1. This is state 2. Here we have constant volume, so this is a closed system. There is no inlet and exit. There's only a change in the phase within the control mass. We call it control mass, no? Closed system. Not control volume, control volume refers to open system. So there is no mention of accumulation. Therefore, we can say that our scenario right now is steady state. No? Other assumptions, aside from steady state, um, kinetic energy and potential energy are negligible. There is no mention of any velocity or elevation. What else? Can we assume ideal gas? I don't think so. According to the tables, there's water there, no? So we have thermodynamic data for water. Therefore, we don't need to assume the substance as ideal. I have another question. In this scenario, do we need an entropy balance? Second law of thermo. No, because we don't have any isentropic efficiency information. We don't have an assumption that the process is reversible. So, yeah. I think if we assume gas ideal, then I think the entropy balance is going to be needed. For the time being, state 1. State 1 is characterized by... So, this is a saturated mixture, no? Because we have a quality value. So, what do we do with that? 120 degrees Celsius and a quality of 0.25. Let's bring out, since we have mass, I've emphasized this in the previous video. Typically in this situation, we can, let's go to saturated water in the Sontag tables. Look at 120 degrees Celsius. So, saturated liquid, let me write the formula first. V1, so state 1, equals V1L plus X sub 1 times quantity, 1, V1V minus V1L. What's happening to my stylus? What the hell? Okay. What is V1L? So in Sontag appendix, page 776, V1L 0.001060 plus the quality, then that of the vapor, 0.89186, and then minus 0.001060 again. Okay. Calculate. Okay, so this is the specific volume in state 1. Recall the relationship. We have M1, that is 2 kilograms, no? We can therefore find the volume. Okay, so after that, what do we do now? What are we supposed to look for again? Q and W, no? Heat transfer and work in the system. They're not lowercase, they are capital letter. We are not tasked to look for specific values, specific heat transfer and specific work. Just the normal work and heat transfer, no? So we do know that by the law of conservation of mass, M2 is also equal to 2 kilograms. What can we do with that information? Also, this is a closed system, constant volume. So volume 1 technically is equal to volume 2 as well, right? Okay, so we have something. M2 is 2 kilograms, no? By virtue of law of conservation of mass. So V2, specific volume, is going to be what is that equal to? 0.22376. Okay, so what now? We need, in state 1, we also need internal energy. Okay, so 120 degrees Celsius, no? Internal energy 503.48 plus 0.25 times quantity. That of the vapor, 2529.24 minus 503.48. Calculate. (1,009.92 kilojoules per kilogram). This is specific internal energy. By the way, work is equal to, we are looking for capitals, no? Capital work is equal to negative P dV. no? Um, okay, so in that case, this has to be multiplied to the mass flow rate so that the unit, both left and right, is going to be kilojoules. Do we have a pressure value? We don't. Wait, so since our process is constant volume, dV is equal to 0. So this one is 0. Therefore, the work is equal to 0. Okay, so in that case, there. Q is simply just this one. No? This one. So let's find U sub 2. Do we have information for U sub 2? I mean, quality rather. Because we're not sure about the condition in state 2. All we know is 140 degrees Celsius. But what do we do with it? At 140, 0.223 V sub 2 is within VL and VV, no? So we're expecting that this is this is still saturated mixture because the specific volume 0.22376 is in between the values here, no? Let me actually point that out here. So at 140, we have 0. Wait, this is specific volume, no? Specific volume. You see 0.001 and 0.51. Somewhere between, we have 0.2. So we can confidently say that state 2 is a saturated mixture. So what do we do now? V2 is equal to V2L plus quality X sub 2. That's exactly what we're gonna find. Sorry. Okay, so 0.22376 V sub 2L 0.001080 plus X sub 2. Basically, we're just gonna do shift solve, no? Okay. 0.22376 equals 0.001080 plus X times quantity 0.550885 minus 0.001080. Shift solve 0.4385. So now that we have the quality information for state 2, we can use that to calculate for the U sub 2, no? U sub 2 is equal to U sub 2 liquid plus X sub 2 times quantity U sub 2 vapor minus U sub 2 liquid. Okay. So also in the same page, page 776, besides specific volume is internal energy. That is what we're gonna write. So 588.72 plus 0.4385 times quantity to 550.02 minus 588.72. Okay, calculate. 1448.75 meter cube. Sorry, this is internal energy, so kilojoule per kilogram. By the way, just a side comment. Kilojoule is, has units of kilopascal meter cube. Best you memorize that. Okay, so we have U1 and U2. Let's go back to the energy balance. So our Q, what we're looking for, is equal to, what's the mass flow rate? Basically just 2 kilograms. Sorry, this is not mass flow rate, just the mass. Okay. U sub 2, 1448.75 minus U sub 1, this one. Calculate. $877.66. The unit here is kilojoules per kilogram. So cancel kilogram, we have kilojoules as the unit. That is the unit for total heat transfer. For the work, this is actually our answer already for that, no? Because our process is constant volume. So dV is 0, therefore work equals negative PdV is also 0. Verify. Yeah, basically 878 kilojoules. How about our work? Let me check if we got it right. Okay, yeah. Okay, so that's it for this problem. Let's move on to the next one. So number 2, wait. I'll just get my glasses. I'll be right back. Okay, so a rigid tank is divided into 2 rooms by a membrane. So let's draw a rigid tank. We're gonna divide this into 2 parts. So we have a membrane that divides it. Okay, so we have room A, then room B. Both contain water, so water is our substance. Room A is at 200 kilopascals. We have a specific volume information, 0.5 meter cube per kilogram. And then the volume, VA, is 1 meter cube. And in room B, it has a mass of 3.5 kilograms. Pressure is 0.5 megapascals, 400 degrees Celsius temperature. The membrane now ruptures. Okay, sorry. We're not gonna draw a big diagram. It's not gonna fit. We need, we're basically gonna have this state 1 and state 2. It's too big. Okay, so this is state 1, state 2. What are the characteristics for state 2? Membrane has already ruptured, so no more boundary. Water comes to a uniform state at 100 degrees Celsius. Find the heat transfer during the process. So, okay, so this is our given. We have our required. So just Q, heat transfer. So first things first, material balance. Is the process steady state or transient? In this scenario, our process is steady state. There is no mention of accumulation. So M1 is M2 is MSS. And then assumptions, negligible KE and PE. This happens very often as far as from my experience so far. Because there's no mention of velocity and elevation. So yeah. Aside from that, any other assumptions? I don't think there are any other. We'll just leave it at that for now. Okay, energy balance. Is this open system or closed system? There are no inlet-outlet streams mentioned, so this is a closed system. Therefore, we use internal energy at the left side, and on in the other side, we have Q plus W. Is there heat transfer? We don't know. That's what we're looking for. Do we have work? Work is zero if the process is isochoric or volume is constant. But I don't think we know that information yet. So we'll leave it at that. For now, let's go here. State 1. Okay. So we have, technically we can already calculate for, since, sorry. VA is equal to VA over MA. We can calculate for the mass in room A. Volume is 1 meter cube divided by 0.5 meter cube per kilogram. What's that? 1 divided by 0.5, that is 2 kilos. Okay, so recall in room B, there. So that means M sub 1 is equal to 2 plus 3.5, 5.5 kilograms equal to M2 by virtue of law of conservation of mass. Okay, so we already have the masses sorted out. What do we do next? We have a pressure, no? 200 kilopascals in state 1. Wait. That's for room A specifically. Oh, okay. What do we do? At 200 kilopascals, let's determine the state of our room A. If it's a saturated mixture, we might get something from it. So everything here is under state 1. Huh? page is pressure entry for saturated water, 200 kilopascal. Pressure entry 200, page 780 in Sontag. So 0.001061 plus x sub a is what we're looking for. V sub a is what again? 0.5. We'll put that there. What is the vapor? Saturated vapor 0.88573. Okay. Calculate. One zero six one. Okay, so there is quality, no? We're able to prove it. The question now is, maybe that could be useful later on for something. For room B, 0.5 megapascal, 400 degrees Celsius. What is 0.5 megapascal in kilopascal? 0.5 times 1,000, 500 kilopascal. What is the temperature? 400. Let's go to page 785. Yeah, page 785. 400, sorry. Yeah, tama. 5 kPa, 400 degrees Celsius. So V sub B is equal to 0.61728 meter cube per kilogram. What else can we find? Do we know the mass of room B? Yes, we do. So recall, M sub B is equal to 3.5 kilograms. Verify? Yes? Okay. So therefore, we can find volume of B, which is VBMB. 0.61728 times 3.5. 2.16 meter cube. That is the volume of room B. Okay. In that case, what is the volume for room A? One meter cube. So therefore, the volume of state 1 3.16 meter cube. I think that's gonna be also the volume for state 2 since this is a closed system. Yeah. It says rigid tank, sorry, in the problem statement. Rigid tank. Therefore, that is equal to volume 2. Since rigid tank, again, recall the formula for work. Work is negative P dV. dV equal to 0. Work is 0. So work is 0. Q is equal to mass times u sub 2 minus u sub 1. There, our plan is now much more clearer. This one will have to do with finding u sub 2. For the time being, we know this mass is the one that we found earlier. That is the m sub 1, no? Which is also m sub 2, since this is a steady state according to the law of conservation of mass. U sub 1 could be found already. How? To find u sub 1, uh, what's the... What is the mass 1? That is 5.5 kilograms, no? Let's see if this works. 0.5745. U sub 2 minus U sub 1, and we have a mass. At 500 kilopascals, what is the... Let's go to pressure entry. At 500 kilopascals, enthalpy, no, specific volume, 500 degrees, sorry, kilopascals rather. I think I'm gonna stop right now. maybe this is what we're gonna do. Actually, let's try that. Also, under these conditions, 500 kPa, 500 kPa and 400 degrees Celsius. 2963.19. This is kilojoules per kilogram. With this, U sub 1A is equal to 200 kilopascals. Let's go back to pressure entry. At 200 kPa, let's look at internal energy. The liquid is 504.47 plus the quality. Two five two 9.49 minus 'This is pretty new. It's kind of contradictory to the principle we've been abiding to, but this is a pretty weird scenario. The corresponding masses of rooms A and B are different, so we cannot just say that mass is multiplied to each of them. So mass 1A and then mass 1B. U sub 1A is 1646.58 times 2 kilograms. Don't forget the unit, kilojoule per kilogram. So the unit you'll end up with is just kilogram. Kilojoule rather. U sub B to 2963.19, 2963.19, and then 3.5 na. So 13,664.33 kilojoules. That's it. This is not the final answer. It's not boxed, no? For u sub 2, how do we find it? What's v sub 2? We don't, oh, we haven't calculated it, no? I think we have. Same volume, same mass. So at 100 degrees Celsius, no? Let's go to 100 degrees Celsius. Specific volume. We'll find the quality. Oh yeah. V sub 2, 0.5745. Okay. Okay, I'll put a smile there. It's pretty new to me, this part. Okay, x sub 2. Now that we have x sub 2, calculate u sub 2. I don't think we have room A and room B anymore. Yeah, I think that's about it. Oh yeah, this is at page 776. Also, at 100 degrees Celsius, internal energy for 18.91 plus 2506.50. Sorry. One 1134.95 meter cube per kilogram. One 1134.95 times the mass 5.5 6242.24 kilojoules. Okay. I think that's the uniqueness of this energy balance. No, in this scenario, we're not only given states 1 and 2, we also have rooms A and B. No? So in that situation, we cannot say that the mass is the same for both rooms. No? It's possible, but in this case, it isn't. So u sub 2 minus u sub 1. We already multiplied it by the mass. So our under the principle that we have been following since the previous video is still correct. Okay. So we just had to multiply it by the mass earlier. No, we multiplied it by the mass. So Q is equal to u2 minus u1. Calculate u sub 2 minus 13664.33 negative 7422.09 kilojoules. This is a negative heat value, therefore we can say that this is a heat loss. Heat loss, no? Yeah, negative Q. Okay, next problem. So we have um, constant pressure cylinder assembly that contains 0.2 kilograms water as saturated vapor at 400 kPa. How do we draw a piston cylinder assembly? I think this will suffice. I don't know. The figure looks very complicated. I'm not sure if this figure will be enough, but this is it. Piston cylinder assembly. Contains 0.2 kilograms water as saturated vapor. We're given the information on its state or phase at 400 kPa. It is now cooled, so cooling. So the water occupies half the original volume. So V2 is equal to half of the original volume. So the required is find the heat transfer in the process. Half the original. Constant pressure, okay. So that's also a detail, constant pressure. Isobaric, yeah. LCM. There is no accumulation information mentioned, so we assume this is steady state. Assumptions. Negligible KE, negligible PE. P is constant. What else? In the FLT, this is piston cylinder assembly, so closed system. Therefore, in our energy balance, this is still delta U. Delta U equals Q plus W. Is boundary work involved? Constant pressure. Work is negative P dV. Pressure is constant, it doesn't change anything. So work cannot be zero. No? So we'll leave it as is. What else? We have information on the first state. Let's work on that. State 1 is 400 kPa saturated vapor. We can identify the specific volume from those two information, those two ideas, and since we have mass 1, we can identify volume 1. Volume 1 is M1, specific volume 1. Specific volume, what page is that? Pressure entry, no? 400 kilopascal. Sorry. Pressure entry 400. Pressure entry 400. This is water, no? The substance. Okay. 400. Sorry. This is not a mixture, so we don't whip out the formula. Okay, so what? We were able to find the volume, so what? We need internal energy eventually for later. Let's find U sub 1. 400 kPa saturated vapor. 2553.55. Okay, we'll need this later. So we are able to find the volume 1. 0.5 times volume 1 is 0.046246 meter cube. Constant pressure, so still 400 kPa in the other side. By law of conservation of mass, it's still 0.2 kilograms in the other side. We have mass 2, we have volume 2. Let's find specific volume 2. At 400 kilopascals, 0.2, 0.23. Okay, state 2 is between VV and VL. So state 2 is saturated mixture. Now, since we have V2 and we know the pressure, 400 kilopascal, we can identify the quality. Zero 0.23123. 400 kilopascal, no? In specific volume. Yeah. 0.001084 plus what we're looking for, the quality at state 2, 0.4 0.46246 minus 0.001084. Okay, so what is the quality at state 2? 0.23123 equal to 0.84 plus x times quantity 0.46246 minus 0.001084. Using that, yeah, we can find U sub 2. So U sub 2 is equal to, also at 400 kilopascal, liquid plus quality liquid here, vapor 2553.55. Okay, so we have U sub 2 and U sub 1. What is the work? Okay, so I think I know what to do. W is negative PdV, no? Pressure being 400 kilopascals. Volume 2, volume 1. What is our volume 2? Volume 2 is 0.046246 minus volume 1. Volume 1 is 0.092492. These, look at these two. Negative 400 times 0.046246 minus 0.092492. 18.50 kilojoules. Yeah, kilopascal meter cube. That's the importance of what I said earlier. Memorize this for that exact reason. This is kilopascal, this is meter cube. Kilopascal meter cube is kilojoule. And since this work is positive, this is work input. Yeah, work input. Whoops. But that's not what we're looking for, no? That's not the final answer. So Q is equal to delta U minus W. From here, no? The energy balance. What is wait. State 1 and state 2, do they have different masses? No, no. So yeah, sure. This has to be mass times, okay, minus W. Mass is what? 0.2 kilogram. What is U sub 2? 1576.58 minus. we are done. Yeah, that is... since the Q is negative, this is heat loss. Heat leaving system. Yeah, okay. I feel like problem 3 is easier than problem 2. Mm-hmm. Okay. Let's go to problem 4. Okay, so a nozzle, okay, nozzle, you draw it like this. Sorry. This is just a crude drawing. Don't use this as a primary reference. A nozzle receives a... So this is inlet, this is exit. Receives 0.1 kilograms per second steam at 1 megapascal. Let's make this kilopascal already. 400 degrees Celsius with negligible kinetic energy. The exit is at 500 kPa, 350 degrees Celsius, and the flow is adiabatic. That is, Q is 0. The heat transfer is 0. Find the nozzle exit velocity. Okay, so this is the required. Nozzle exit velocity and the exit area. Okay, I think this is where we have to summon these formulas. I did not mention this in the first video, so I'll mention it now. Area is 4 pi something. What's area to diameter? Pi d squared over 4. We're gonna need this specifically if diameters or areas are not the same. Somewhere along those lines. So I'll put a highlight here. Yeah. LCM. Is the process steady state? There is no mention of accumulation, so this is gonna be steady state. Assumptions. So it's already specified negative kinetic, sorry, not negative, negligible KE, negligible PE as well, because there's no mention. What else? Adiabatic, so Q is 0. So far, those are the most obvious ones, no? Let's go to FLT, the energy balance. Is this process, is this system open or closed? Nozzle. This is a nozzle. Shaft work is 0. I can't remember the formula. Never mind. I'm not sure how this formula applies. Anyways, yeah, this is nozzle. No shaft work. This is open system. No. This nozzle is a thermodynamic device. So for FLT, no longer internal energy, this is delta enthalpy. Okay? Q is 0. No? Let's make this. There you go. So it's gonna be like this. What are we supposed to look for? Nozzle exit velocity and exit area. Oh yeah, velocity is involved. So mass flow rate is density, area, velocity. Or since density is the inverse of specific volume, it's gonna be like this. Volumetric flow rate, on the other hand, is just A times the velocity. This is the d over dt volume. This one is d over dt m. Why would this be important? Yeah, so area. We'll go back to that later. For the time being, what we can do, state 1, 1000 kilopascal and 400 degrees Celsius. What can we find here? Wait, what's the substance here? Steam. Huh? Steam. So technically this is still water. By default, steam is water. 1000 kilopascal, 400 degrees Celsius. Let's try enthalpy. What's state 2? 500 kilopascal, 350 degrees Celsius. Okay. Technically, we can look for work already. 3, I think. But wait, don't know the mass. I suspect there's something wrong with my energy balance. Yes, there is something wrong with my energy balance. Let's go to Smith, page 266. The answer lies here. One over 2 internal energy squared. What is the KE value? Sorry, V squared. Sorry, I made also a mistake. Another one. Work is 0. That's always gonna be for the case of a nozzle. Why? I've already mentioned it earlier. The shaft work for a nozzle is 0. So the work here is 0. Ay, ay, ay. Why was I able to miss that part? Okay, anyways, moving on. We want to find velocity. According to the problem, in the inlet, KE is negligible. So, there, velocity 1 is 0. Let's bring the FLT below. Actually, wait. Yeah. Since V sub 1 is 0, okay, let's find V sub 2. H sub 2, we already found it. Okay, 3167.65 plus 0.5 times 3263.88, 13.87 meter cube per kilogram. Let's bring out this formula. Wait, I got it wrong again. What? Three, two, six, three. Oh. I think I forgot the formula. Wow. Kilojoule times 1000. Sounds about right. So I made another mistake here. So this is in kilojoule. This is also in kilojoule. In dimensional analysis, also I got the unit wrong. This is supposed to be uh, meters per second. If velocity has units of meter per second, h should have units of joule per kilogram, not kilojoule. For an FLT of nozzle, which is typically h2 plus 1/2 velocity 2 squared equals h1 plus 1 over 2 velocity 1 squared. So these are the rules that you have to know if you encounter a nozzle thermodynamic device, such as what we're encountering right now. So as a result, we're gonna have to convert 1 kilojoule 1000. We just multiply 1000 both sides. So as a result, we have 438.70. 438.70 for the initial velocity. What are we looking for? Exit velocity. That is our V2. This is one of the answers already. And then area E. So the area. We can say that exit and state 2 are the same, only if our process is steady state. In transient, no, that cannot. Exit and state 2 as well as state 1 and inlet are different things. Okay, we can only interchange these notations in steady state processes such as what we're encountering right now. So what's the mass flow rate? What's the specific volume to? This one, no? And then velocity, 438.70 meters per second. We're expecting meters squared as the unit here. One, two, three, four. Meters squared. It's kind of weird as a number if you leave it like that. So convert to centimeter. Okay. So we're good. I'll stop the video here. Yeah, I'll stop the video here. We'll continue in the next video.